All right, so this is going to be 15.3 double integrals in polar coordinates. So the last problem that we just did in the previous video was a really tough problem because the limits of integration were really funky. And polar coordinates are going to be really helpful for us because it'll kind of reduce that problem into something nicer. So you'll see, well, we do that problem with polar coordinates, and you'll see how easy that problem can be when we convert to different coordinates. And as a matter of fact, we're going to see some other coordinate system when we look at triple integrals, and it'll make the problems also a lot nicer. So let's recall a little bit of polar coordinates. So this is stuff that you probably have seen before in Calc 2. So for one, here is a formula for the polar coordinates. So we got r squared equals x squared plus y squared, x equals r cosine theta, y equals r sine theta, and theta equals tangent inverse of y over x. All right. So this is kind of how we were able to convert from polar back to rectangular units. So why convert to polar? Well, usually you have these regions that are kind of really hard to integrate. So you see, if this is a region, you can see that you would have to take this lower part of the circle and this upper part of the circle as the limits of integration. And even if you wanted to do the opposite way, either whether you were doing a case 1 or maybe even a case 2, you'll see that it's still really hard, because if you solve for y, you're just going to get y equals plus or minus square root of 1 minus x squared for this example. So dealing with these limits of integration can be really, really difficult, if not impossible. So later on also we'll see regions between two circles where it's just as equally difficult, because now you have to deal with two different square roots. So that can be a little bit tough. So one of the ways to do it is just to convert to r and theta, because if I can parameterize this particular circle into polar, so r is now going to be a radius of from 0 to 1, r represents a circle of radius 1. So whenever you think of r equals 1, that's a circle of radius 1. R equals 2, that's a circle of radius 2. So converting it this way would be a lot easier to work with as opposed to dealing with the entire circle. So let's say we want to evaluate the double integral of f of x comma y dA, and R is one of these regions. So it can be either a circular region or a region where you might have to do like some sort of square roots. And let's say that R can be described by polar coordinates such that R can be between A and B. So maybe this example where you have two circles, and theta is just an angle from alpha to beta. So you can see that the radii can just change. So this will be kind of like a circle of radius 1 and a circle of radius 2. And then theta can be like from 0 to pi. And you can see that if I take the integral, right, from 1 to 2, this guy will take care of the circle part, circular part. And then theta being from 0 to pi will take care of the angles, right? So doing so can actually really make the limits of integration really nice, because now we will have to be doing a double integral where the limits of integration are integer values, or some real numbers, I guess, because you have pi. So let's say we can easily describe this in polar coordinates. So what we're going to do is, let's say we have a polar curve. So this polar curve looks something like this. So maybe it's a part of a circle. And we have theta equals alpha and theta equals beta. So from an angle from one to another. We also have two radii. So we have radius equals A and radius equals B. So this will take care of the radius of these particular circular regions. All right. So what we're going to do is very similar to how we did Riemann sums. So we're going to divide all of these little regions into little rectangles. And the purpose of this is that we want to be able to find the area of one little subsection, because then we can add them all up, take the limit, and that will give us the area of this entire thing. So we're going to let R be b minus a divided by m. So that's just me making them into little small circles. We're dividing them into little equal rectangles. And then we're going to also let theta be broken up into beta minus alpha divided by n, where n will be the number, n and m will here be the number of rectangles that you have. So here we also have the r values go from, let's say r equals ri. So this is just saying like this is the first one, this is the second one, this is the third one, third radius. So you can see that you have many radii here. So the purpose of this is to be able to find the area. So we have to recall a formula from trigonometry, which is probably you might have forgotten, and the area of a sector. So the area of a sector, basically what it does is that if you have a circle, right, and you have a radius, okay, and then you want to find between two different angles, two central angles, then here we want to be able to find this particular area. Okay, and the formula for that will be area is equal to 1/2 r squared times theta. So this is from trigonometry, so from trig. Okay, you might have seen it also in Calc 2, so this is also where this formula also comes from. All right, now notice that finding the area of this thing, let's say this little square, what's going to happen is that I'm going to end up finding the area of this entire section from there all the way to there, which is not quite what I want. I don't want all of this area. This is the area that I don't want. What I really want is this particular area, this one. I want to find this little small area. So what I'm going to do in order to find that little purple area, what I'm going to do is I'm going to find the area of this guy from this whole thing, from here to here. Find this area. So this is going to be from a circle of radius ri. So let's say this is the ri'th radius. And I'm going to subtract this whole area. So right here we have this purple area. And what I'm going to do is I'm going to subtract the area of the I minus 1th circle. So for example, this guy. So I'm going to subtract this area. So you can see if I take the purple area and I subtract the bluish area, what I'm going to end up with is this area that I really wanted. Okay, so that's the whole purpose of this. So all I got to do is just plug in Ri in here and subtract it by Ri minus 1, which is kind of what I did here. So the area, the change in the area would be the 1/2, the outer one minus the inner one. Okay, so you can kind of think of outer minus inner. So here, one of the things that you can notice is that you have a delta theta, right? Because delta theta here is going to be the change in the theta value. So you can see that in order for me to find that, you're going from theta, oops, wrong one. You're going from, I'm running out of colors. You're going from theta 1 all the way to theta 2, or I'm going to say theta I minus theta j. Theta I or theta I, oh, I'm sorry, we have theta j. So theta j to theta j minus 1, which is basically delta theta. So it's just a change in the thetas. So that's where that delta theta came from. So we can factor this guy out. And you can see that you got the factored form here. And now what we have here is that we can go ahead and factor, so we factored out the delta theta, and we can further use a factor form of this guy. So this is just a sum of squares. So if you recall from algebra, a squared minus b squared, this is just equal to a plus b, a minus b. So that's where this guy came from. All right. Now notice here that if I subtract ri minus 1, which is basically from this ri minus, and then this ri minus 1, that's just a change in the r values. So it's how much I'm changing. So this is called delta r. So delta r will be the changes of these little small rectangles. So that's where this, so we can see that this guy right here is just going to be delta r. Okay. Now, one of the things that you can notice is that this guy right here, let me highlight it, it's just going to be a midpoint. Okay, because that's just a midpoint formula. So 1/2, I'm taking half of the sums of the two guys. So you're actually, this guy's just going to be a midpoint. And this midpoint, we're just going to call it Ri star. So if you go back up to the graph, let me go ahead and delete this part. You'll see kind of like a little dot here, and that's where that dot is at. This is in the middle part. So this is just a midpoint. So that's why we're going to call it Ri star. Okay, so basically I'm going to replace this highlighted part with Ri star. Okay, so that's where this guy came from. So we got Ri star delta R delta theta. Okay, so basically the area, or the change in the area, should I say, is going to be equal to this guy. So we've kind of reduced it from something that we started off with to something that is a little bit more known. So now what we're going to do, remember this is the formula that we wanted to go ahead and convert. We know that x is equal to r cosine theta, so that's where this Ri star cosine theta j star came from. Same thing with the y, that's just Ri star sine theta j star, and dA is going to be the change in A. But now I know what change in A is, right? Change in A is just that guy, so what I'm going to do is I'm going to plug in this Ri star delta R delta theta in there. So now, all we got to do, remember this is an approximate value, so this is approximately equal to the double integral. So in order for me to just make it more equal, all I'm going to do is take the limit as m and n go to infinity. So I make them really, really small. I make all my subsections really, really small. And what's going to happen is that the summation is going to turn into a double integral. And the double integral is going to be wherever the limits of integration of r is. So you can see here is delta r. Oops, that's not what I wanted. I wanted this. So we got this Ri. Oh, no, not that Ri. This delta R. This delta R is going to be these guys. So that's the radii, the change in the radii from radius 1 to radius 2. And then you can see that our delta theta is going to be the changes from both angles, from one angle to another. And then all we really got to do in order for me to find the integral, to find this type of integral, which was really hard to do, if I wanted to make it a little easier, all I got to do is plug in the x values, replace them with r cosine theta. The y values, replace them with r sine theta. Now, here is the crucial part. There is an extra r in here. So you see that there's an extra r. So when you're converting, not only are you just immediately plugging it in, but you also have to add this extra r. And sometimes it's commonly forgotten, so don't forget about that guy. And once you have that, you can just integrate with respect to r and integrate with respect to theta, which is actually pretty nice. All right, so here r, remember, is just the changes in radius, and theta is going to be the changes in angles. So in order for me to go ahead and do a double integral, if I want to do a conversion, again, replace x with r cosine theta, replace y with r sine theta. You'll have an extra r, and then you just integrate with respect to dr and d theta. All right, so this was a little bit of a derivation. In the next video, what we're going to do is do 2 examples to kind of get used to converting to polar.